Good afternoon, everybody. Many thanks for joining us for today's Tech Talk. Today's Tech Talk is about slab strengthening using carbon fibre to strengthen an existing slab. I'm Steve Musa, one of the operations team. I'm joined today by our technical director. This is a technical presentation. Jayesh, good afternoon.
Good afternoon.
So we're here to talk about slab strengthening. So the first thing I just want to go through is what our itinerary is today. We're going to look at very briefly why would you use carbon fibre, the slab strengthening itself. We've got some nice examples for you to look at, and then at the end, if there's any questions that you have, you can email or drop us a line. So let's jump straight into it. So we're looking at why use carbon fibre. Why would a designer look to use carbon as opposed to concrete and steel, Jay?
Right, so carbon fibre strengthening is becoming quite popular these days, and it's also now a go-to method first engineers and architects check for. The reason for that is that carbon fibre is a very high strength and lightweight material which is used for strengthening concrete, steel, wrought iron, cast iron, even on timber structures. So just to give you a feel in terms of number, carbon fibre is at least 3 to 4 times stronger than steel and at least 7 to 8 times lighter than steel. So you could see strength to weight ratio and why people prefer to use FRP over traditional methods. The reason for that is that it's much quicker to apply as compared to any other traditional method of steel or concrete. For that reason, it is becoming quite popular these days.
Yeah, I think it's a bit of a misconception as well. People think that it's a relatively new technology, and it's not, basically, is it?
No, this is clearly a misconception. It is new as compared to concrete and steel because they've been in the industry for 100 odd years or even more. The carbon fibre was first used in 1944 in aerospace engineering. Then they started making all the aeroplanes, fibre boats, motor cars using FRP. And then in 1988, this was first used in construction. And after that, it was quite commonly used since then. So it is, you could see it is at least 35, 37 years old technique. So it's not that new, but compared to concrete and steel, it is still new technology.
And generally speaking, over the last few years, our go-to clients are structural engineers, but we're seeing a bit of an upsurge from main contractors looking to, because it's quite an economical solution.
It is, yeah. So if we see the whole cost of carbon fibre strengthening, which includes material, labour, disruption to your structure, and most importantly, time in doing that strengthening, then carbon fibre strengthening will be the most economical solution. But generally what happens is that people just compare the cost of carbon fibre with like-for-like cost of steel or concrete, and they sometimes find it expensive. But that's not the reality, because even if you're applying concrete and steel, you have to put it in place and apply it in position. As the same thing with carbon fibre as well. The money we save in carbon fibre is mainly in time, because it's much quicker to apply and very easy to install as compared to any other traditional methods.
Again, I think that's we've proven quite on several times projects where we're able to drastically reduce the program times because of that.
Yes, exactly. Yeah, because generally the traditional construction works around concrete and steel, so they have program times accordingly. But when carbon fibre system is introduced, it is much quicker to apply. So that's where they actually save a lot of time.
Okay. So we'll go into a bit more detail now, the sort of slab strengthening in itself, and we're going to show some projects that we've worked on quite recently in the UK.
Yeah, so we'll talk about the slab strengthening. So generally, slabs are, as we all know, they are flexural members. So they are generally strength for flexure only. So as you could see in picture 2, there is an image showing carbon fibre applied at the underside of the slab. That is generally to strengthen for sagging moments. Picture 3 shows the application on top, which is for strengthening for hogging moments. And also, up to an extent, slabs can also be strengthened for punching shear, which is the picture 1, as you could see. So that is the slabs around the column area strengthened using carbon fibre to improve the punching shear resistance of the slab. So these are the 3 main requirements for which generally the reinforced concrete slabs are strengthened. So if we try and understand it in a very simple schematic, that how the carbon fibre strengthening works, or what's the concept behind strengthening using carbon fibre, then this is a very simple schematic diagram which shows how the carbon fibre is applied and its purpose. So one thing to note here is that carbon fibre has very good properties in tension, and it is always recommended to be applied onto the tensile face of the element. So for that reason, it is applied at the underside and the mid-span, as we can see in the image. That is to improve the sagging moments or positive moments. And it is also applied on top near the supports to improve the hogging moments or negative moments. So again, as we can see, it is only applied onto the tensile faces of element. Carbon fiber is not recommended to improve the compressive resistance of the element, especially in a section analysis. The reason for that is that carbon fiber is a very low profile material. So like I said, typical thickness of carbon fiber is around 1 millimeter. So it doesn't give you significant improvement in the section modulus. So it doesn't improve the compression significantly. That's why it's generally or mostly applied onto the tensile faces of element. But there is another key detail or construction detail which many people miss out, especially for hogging moment strengthening. So whenever they are doing hogging moment strengthening, they apply FRP on top of the slab or the beam and take it up to the ends of that span and then stop it there, because there will be a column in the way or a wall there or something. The reason is that you cannot continue FRP beyond that point. But in reality, that's the point where we are going to have the peak stresses. So if we are stopping or curtailing the reinforcement at the location of the peak stress, technically there is no point in doing that strengthening, because that's the location where we need the strengthening the most, and it will not be effective at that location. So it needs some sort of anchorage detail there, or a development length, or some sort of detailing there to transfer the force back into the ends and support. So we can do that by using carbon fiber anchors drilled into the columns or into the wall. Or some people may also do, lap the FRP up to the column face and put a hoop around the around the column to provide that sort of development length. So that's how the actual hogging moment strengthening is done. And there is an image shown of the anchor there, that how these anchors are used, which we'll talk about in more detail on further slides. So generally, these anchors are used for, there are two types of anchors. So one is used for construction detailing, which we've seen like the small anchors. Then we also have bigger anchors, which are specially designed anchors. So the small anchors, how we use them is that we drill a hole into the concrete, we saturate the anchor, put half of that anchor into drilled hole, which is filled with epoxy, split the remaining half on the face. So after that curing, it becomes one unit which will cure simultaneously, but it is actually going into concrete, so it provides you additional anchorage or bond capacity. So your debonding or delamination failure will not happen. So that's how those nominal anchors are used. Then these bigger anchors, or super anchors we call them, they are specially designed anchors for a particular force. So whenever we are doing design, we know the force at the end there, so especially in the hogging moment detail, and then we'll design these anchors to carry that force through that obstruction or into that obstruction to transfer the force back into the wall.
So this is the anchor which is shown in picture 3, yeah?
Yes, this is the picture 3. So the guy is holding that bigger anchor prior to installation, then we saturate it. So there is an example given in picture 1 and picture 2. So picture 2 is basically a slab strengthening example, which we strengthen for hogging moments. There was a column in the way, so what we did was we drilled hole through that column, used these bigger anchors, pass them through that drilled hole, and then splay it on both sides like a dovetail. So after curing, it becomes one unit, which will actually, becoming as a tie, which will transfer force from one side to another side. So that's how these anchors are used. So this is the correct way to do strengthening on top of the slab, or hogging moment strengthening, because we've got a continuous top reinforcement in that location. The similar sort of detail is shown in picture 1, but that's a vertical element. So we are strengthening there a shear wall, and the obstruction there is coming from the slab. So in that instance, we applied the FRP vertically onto the wall, and we drilled hole through the slab to transfer the strengthening from floor above to floor below. So that's how those anchors were used. So these bigger anchors are used to transfer force from one side to another side.
And these are the larger anchors, the super anchors in picture 3, they're all individually designed specifically for a particular type of requirements, basically.
It is, yes. So as I said, that when we design it, we know the force in the FRP in that location, and to transfer that force, we'll design these anchors. So the actual diameter of anchor, density of the anchor, length of them, and everything will be designed.
Okay. So we're going to look at a specific project now. I think this is one of the biggest projects that we've worked on quite recently over the years.
Yeah, so it is Blythe Road from Hayes and Harlington in London. So in this as well, it's also an example of strengthening a new build structure. So we could see in picture 1 the overall structure which we strengthened. So there were 3 tower blocks, A, B and C, we could see at the back. They were 11-story tower blocks. The reason for strengthening was that, as I said, they were new builds. So the frame was constructed in 2014, But after the construction of these frames, the contractor who was working there has gone into administration. So before passing his work to the new contractor, there was some structural investigation done just to, as a due diligence, to make sure everything is as it should be. So when they scanned these flat slabs, they found that there is some rebar missing in those flat slabs. And there was not just one area where the rebar was missing. It was around 400 plus areas where the previous contractor did not put the required reinforcement.
Wow.
So the structure got condemned. The client was asked to demolish and rebuild. We all can imagine the demolition cost of this structure, let alone the rebuilding. And also the money they have spent to come up to this stage will be of no use. So we worked with new consulting engineer there and then designed each individual area for the lack of reinforcement and applied equivalent amount of carbon fiber. So it was a quite involved kind of design.
So on the design side, then how did we took the client's information and we then produced. We actually worked on every individual area that was required.
Yes, so as I said, there were 400 plus areas. So I think we were able to do around 385 areas with carbon fiber.
Yeah.
So the information came to us in form of like finite element analysis output and some markups from structural engineer, which we could see on the screen.
So this is the information that the client provided to you and your design team to take away and work. Bring up a solution there.
Yes, on this you could see that client has mentioned that what the reinforcement should be, whether it is applied correctly or not. So in some instances it was failing in extents. So they applied the required reinforcement but not to the required area. They applied it in very small area, so it needed extending and everything.
Yeah.
In some instances the rebar required was 20 millimeter diameter, but they only used 16 millimeter there, so that was another kind of failure. So this type of information came to us for individual floor levels, individual areas and everything, and we took that up and then did our own design. So this was kind of the output which we produced. So there were individual areas which we marked on a key plan which needs strengthening, and then there was a detail shown for every area that how much carbon fiber needs to be there, what sort of anchors we are applying and everything. For example, this is the area which is shown near grid line P, marked as area 3. So in this instance it was failing in extents, and then that's how we designed it. Because it was just failing in the extents, our FRP was mainly outside of the column, but there was some carbon fiber going through the column. That's why we used carbon fiber anchors there, as you could see on the drawing there.
Yeah.
So that's the kind of detail we produced. So as I said, it was quite involved design. We worked very closely with project engineer there and designed each and every area individually there.
Okay.
And these are some of the images of the application you could see. So generally the strengthening was around the column areas only, because what the previous contractor did not do is that he did not apply the additional mesh which we generally put in a flat slab situation around the column area for hogging moments and punching shear. So that was missing. So generally the carbon fiber was applied was in the column areas only, and that's how it was applied. And also because this was very important structural retrofit using carbon fiber, and carbon fiber was needed in fire limit state loads as well. So fire protection system was applied, as we could see in the rightmost picture there.
I think it's a key point to note this about the fire protection side. It's a bit of a misnomer. People think you can't fire protect carbon fiber, and you actually can, yeah. Yeah,
carbon fiber can be fire protected. On its own, carbon fiber doesn't have any inherent fire rating, but if you want fire protection, you can apply additional coatings or systems on top of it to get the required fire rating. In this instance, we use the cementitious fire protection system, which was basically tested for up to 4 hours fire rating. So there are tested and approved systems available in the industry. So if needed, carbon fiber can be fire protected.
That's great. So we're going to look at very quickly the application process, because obviously the preparation, the application of carbon fibre is as critical as the design. If it's not done properly, you're going to have a problem. Yeah, and for that very reason, we do not subcontract this part. It is done by our own guys, which are employed by us. So everybody is trained by us to apply this, and we don't give it to any other subcontractor to apply this on site, because as you said, this is the most important part in carbon fiber strengthening. So it is some different stages of application. So first thing is surface preparation, which is mostly in building environment. It is done using diamond grinding, followed on by cleaning. So you need to clean the area so it becomes dust free. Then you do priming, which is usually done using pure epoxy. So the reason for using pure epoxy is it can soak into concrete and give you a proper key and bond.
Then you apply first coat of thickened epoxy, which is the white color epoxy you've seen there, and then they unroll the first layer of carbon fiber. Now the carbon fiber this guy is applying here is actually saturated in a different area on the same side. So when he's applying it in this position or in this place, it is in wet condition. So that's why this application is called wet layup method. And in most of the fabric strengthening application, everyone needs to make sure that the application is wet layup method, because there are still people out there who do dry layup. So in dry layup, what you do is you just prime the concrete using epoxy, then you try and patch a dry fiber with your hand on top of it, and then coat another layer of epoxy on that dry fiber. Now, in doing so, you cannot guarantee the 100% resin impregnation through every fiber, and that dryness will lead to a debonding or delamination failure. So to avoid that, application needs to be wet layup. So that's how we do the application. We apply first layer, then another coat of epoxy, then another layer. That's how we build up the number of layers according to the design. Generally, because this was slab strengthening on top of the slab, you're not limited how many layers you can apply. But if it was vertical or overhead application, you can only apply 3 layers in one day or one shift. After that, you have to wait for it to initially set, which will be 4 to 6 hours. So you can come back next day and apply further layers. So that's how the application is done.
And
After that, yeah, this is the finished section. But after that, if you want, you can screed over it, plaster it, paint it, render it. You can do anything on top of it.
So it's fully cured after.
Yeah, it will be 100% cured in 72 hours in ambient condition. So you can reload your structure back to its new capacity in 3 days.
And again, just to recap, it's a critical part of the process. Everything is done in-house. Our people are trained. Nobody's allowed to go on the site unless they've had this training through your systems.
Yeah, because this is the most important part. You can design it as well as you want, but the guys who are applying on site don't know in which direction to apply and all those things, then it will not work. So for that reason, it is done by our own guys.
Okay, that's great. So that's it. That's our presentation for today. Many thanks for joining us. If you've got any questions, please drop us a line and we will get back to you. Thank you.
Thank you.